Who here remembers what a combustion reaction is? Yeah. What's the combustion reaction? Two plus H2O. Yeah, so those are the products. So CO2 and water are the products. And it's typically a hydrocarbon that reacts with oxygen to produce carbon dioxide and water. So in this case, it's methane, CH4, is reacting with oxygen, form carbon dioxide and water. So pretty much the things that you got to remember for what a combustion reaction, this part can change sometimes of the products, but if it's a carbon-based compound, if this part is carbon-based, then you're going to form carbon dioxide and water. Okay? So yellow is something you could put into memory. The pink part might change depending on the problem. So what's the first thing we should do whenever we're given a chemical reaction, or maybe we have to draw one out like we did in this case? To balance it, right? So is this balanced already, or do we need to balance it? Okay, so how would you go about doing that? We got to use coefficients, right? So where would we place some coefficients? Oh, so we have 4 hydrogens on the left. We got 2 hydrogens on the right, so we can balance those out by putting a 2 in front of water. So that gives us a total of 4 oxygens on the right now. We still have 1 carbon on each side, but we only have 2 oxygens on the left. So how do we fix that? Yeah, so just 2 moles of oxygen react. 1 mole of. So now it's asking for the total mass of the products formed. And 16 grams of methane is burned with excess oxygen. So it wants us to convert to mass of carbon dioxide and mass of water and then add the 2 up. That's what it's asking for, the total mass of the products. So first we would have to start with 16 grams of methane. We always start with what we're given. So what do we do next? Yeah, so you get the molar mass of methane, which is 12 plus 1 plus 1 plus 1 plus 1. So 16. 16 grams for every 1 mole CH4. And then we use what to get to the products? Mole ratio. So the mole ratio, let's do from methane to water first, okay? So what's the mole ratio? Okay. 1 to 2. So for every 1 mole, that's in right here. For every 1 mole of methane, 2 water molecules are produced. So that's where we're getting that from. So 1 mole CH4 will produce 2 moles of water. And now we need to get to the mass of water. So what should we use? So 1 mole of water has mass of 18 grams. Put that into our calculator. I'll have your calculators now. Yeah, 36. That's 36 grams of water. And we would have to do the same thing for the second part. I can just do it really quick. Yeah, so you would get 44 grams of carbon dioxide, and then just add that to 36 would give you 80. So I hope I didn't want to waste time on doing the same thing for the second part, but you would have done the same thing for getting the mass of carbon dioxide. And so when you did all that, 44 or whatever it was grams of. So if there's no questions on this type of problem, we can move to a different kind that requires a little bit more thinking, a couple extra steps. So how many grams of nitric acid can be prepared from the reaction of 138 grams of, how would you name this? NO2. Nitrite. Where's the negative charge? Because nitrite has a negative charge. Nitrite also exists. This thing, are we looking at the same? This one. NO2? Yeah, nitrogen dioxide. That's a covalent compound. If you saw a negative sign, then it would be nitrite. However, nitrite doesn't exist by itself. It's always paired up with the cation to form a salt. So it would be like sodium nitrite. It wouldn't just be NO2 minus by itself. So this is nitrogen dioxide, and that's reacting with 54 grams of water. And so what's the first thing we should do? Anyone? A good guess, but we wouldn't want to add them because they're two separate compounds. So we wouldn't want to get the masses mixed up. Yeah, so we're given the information for two of the reactants. So what should we think about? Limiting reagent or limiting reactant, right? So that's something we always got to think about every time we're given the mass of more than one reactant. So in this case, we're given the mass of nitrogen dioxide and we're given the mass of water that we started with. So we need to immediately think about limiting reactant, okay? So next is how do we find limiting reactant? So we use each reactant and convert that to moles of the desired product. And in this case, the moles of the desired product is nitric acid, right? Because that's what they typically asked, how many grams of nitric acid. So we say, all right, let's start with nitrogen dioxide. 138 grams of NO2.
Wait, what?
Molar mass of NO2 would be 46, I think. 46 grams for every 1 mole. And this is where you would have to make sure your equation is balanced. Give it to us balanced, but it's important to make sure it's balanced before you even start doing all this, because it gets important in this next step. What do we do to get from moles of nitrogen dioxide to moles of nitric acid? Say it louder. Yeah. So we're going to use the mole to mole ratio. And where do we find the mole to mole ratio? The balanced chemical equation, right? So for every, what is the ratio here? Yeah, so for every 3 moles of nitrogen dioxide, 2 moles of nitric acid are produced. Now what? Well, we do actually have to figure out the limiting reactant still. So let's calculate how many moles of nitric acid we end up with for this, for 138 grams of nitrogen dioxide. And then we'll do the same for the amount of water that we started with, which one gives us the lesser amount. So what did y'all get when you put this into it? Got 2? Exactly 2? So that's 2 moles of HNO3. And so I kind of jumped ahead, but I'm already doing the second part. you're going to take the mass of water that you're given, and you're going to convert that to moles of water, because in chemistry we deal with moles, we don't deal with mass. And the only way to get from moles of one thing and is moles of another thing is to go through that mole unit. So you have to go from grams to moles, and then using the what ratio? The mole to mole ratio, we go from moles of water to moles of nitric acid. In this case, that ratio is 1 mole of water, and that produces 2 moles of nitric acid. That makes sense so far, or did I lose anyone? The best time to say something if you got lost. That clarified. Test day, 6 hours, you'll be waiting outside the room. We're all good? Thumbs up? Yeah, perfect. So what do y'all get in the calculator? I'm sorry, I listen to music so loud sometimes, so I can't hear. 5.9933. I'll be honest, I didn't hear you. 5.9. Okay, 5. I thought I heard 5.9, but I didn't know. I didn't want to, like I couldn't hear, but I probably did. So moles of HNO3. Which one's our limiting reactant? Well, HNO3 is not a reactant. Yeah, NO2. So nitrogen dioxide is our limiting reactant. So what you could do is just, since I have an iPad, I can erase things. On a test, I would just cross it out so I don't get mixed up. But since I have an iPad and I need more room, I'm just going to erase all this because we don't need any of that work anymore. So we have 2 moles of nitric acid as our theoretical yield. Now we just need to convert that to the mass of nitric acid so that way we can answer this question. The mass of nitric acid is 3248. 63 grams. If I didn't get the same thing as you got for the molar mass, let me know. I don't have a calculator with me, so I do all this in my head. I tend to make a lot of mistakes. There's an answer choice though, so yeah. Y'all get that too? More stoichiometry or net ionic equations or something different? Net ionic equations, okay. How do you feel now about?
I guess the only thing that confused.
Okay.
I know you gotta use like avocado. Something weird to me, so just later whenever.
Yeah, so let's just do one really quick. It won't take too long. Let's say we're given 26 grams of water. We're asked for, we're given 26 grams of water, and we're asked how many hydrogen atoms are in this specific sample. Not water molecules, we're talking about hydrogen. So what do you think is the first thing we should do? So we're going to get from grams of water to moles of water first. So we know that there's 18 grams in 1 mole of water. So this is the step that might be a little confusing, but it's kind of easy to see once it's done. But does it make sense to y'all that for every 1 mole of water, there's 2 moles of hydrogen? That makes sense with y'all? Right? Because you have 1 water molecule, you have 2 hydrogen atoms. So therefore, if you have 1 mole of water molecules, you have 2 moles of hydrogen atoms. That's where that conversion comes from. And we know for every mole of hydrogen, atoms, how many hydrogen atoms are in that mole? Avogadro's 6.022 times 10 to the 23rd. And your units would be H atoms. So what did y'all get when you put this in? A lot of hydrogen. Yeah, so if you write your units, you'll realize that everything cancels out. So grams of water would cancel out with that. Moles of water would cancel out here. Moles of hydrogen cancels out here. And then you're left with hydrogen atoms as your desired unit. So I really try to emphasize to write your units when you're doing stoichiometry or dimensional analysis, because you'll be able to see, okay, yes, this is canceling out, so I'm on the right tracks. If you don't write your units, then you don't really know where you're going. You don't know what you're converting. Yeah. No, you wouldn't. You wouldn't take into account the molar mass of something for sig trace. All right. Question. All right. Let's do some net ionic equations. Chris, you want to come do?
Love me some net ionic equations. All right. Equations that are ionic, got to do the net form of them. All right. So let's start off with this one, number 9. Cobalt 3 bromide plus potassium sulfate. Well, how many brave volunteers here to give me the chemical formulas of both of these? That is one of them, COBr3. And what is the second one? A2S. A2. What type of reactions are these again? Precipitation or double displacement, double replacement, same deal. All right. So what are my products be? One of them will be a solid. Which one is a solid? Yeah, cobalt 3 sulfide. So it would be CO2S. And apologies, thank you, Nicholas, for that. Should have been writing my physical states. This is aqueous. This is also aqueous. Solid. And where's my last one? ABR. All right. Solid. Question for you. All right. So why is cobalt 3 sulfide my solid? Or what about the S specific? What about this? Is the S normally soluble or insoluble? It is insoluble. Is cobalt one of your exceptions? No, so that's why I would stay as is as a solid. All right. My equation balanced. How do I make it balanced? Here. 2. 3, 1, 6. All right, let's make sure everything's all good. 2 cobalts, 2 cobalts, 6 bromines, 6 bromines, good there. 6 potassiums, we're good. 3 sulfurs, 3 sulfurs. All right, nice. That is indeed balanced equation. All right, that is what we call our molecular equation. So that is our balanced chemical equation. But let's go one step further and do the complete ionic or the total ionic. So to do that, right, we have to split everything up into its ions. So let me write up the formulas for these again. COBr3. All right, so there's 1 cobalt ion, right? And what's the charge on my cobalt again? 3 plus. So CO3 plus. What's my physical state? What state of matter is it in? Aqueous. CO3 plus. This. How many bromine ions do I have? Yeah, 3 or yeah, I should have. Actually, it's 2 cobalt ions, right? Because looking at the balanced chemical equation, I should have moved that. See it a lot better. All right, so there's 2 cobalt ions, right? Because of the 2 coefficient here. There's 2 cobalts, so 2 CO3 plus. How many how many bromine ions do I have now? 6, right? Because 2 for the coefficient and then 3 regularly. So 6 A plus. 6 ER minus. Now, how many potassiums do you have? 6. So 6 plus aqueous. And how many sulfurs? 3 S minus aqueous. Now, do I break up cobalt 3 sulfide into its ions? Yes or no? Why not? That's insoluble. It's a solid. No ions exist. So just write that out as is. CO2S3 solid. Now, how many potassiums do I have? 6 plus aqueous. Finally, 6 Br minus. All right. This pain in the ass was called the total ionic equation. So what do we have to do to get from our total ionic to our net ionic? Yeah. What are those identical ions called? Word for them? Spectator ions. So we're going to cancel out our spectator ions. So goodbye, good riddance. See you later. Didn't like you in the first place. All right. So everybody agrees, right, that potassium and bromine are spectator ions? Because basically the net ionic equation, our end goal is to create our salt, or not salts, our precipitate, our solid. And in this case, there's no potassium or bromine in my precipitate, so I don't need to worry about them. I can cancel them out. All right. Now a brave volunteer, somebody give me the net ionic. The brave volunteers. Yeah. Exactly right. This here is our net ionic equation. All right. Any questions about that? Any at all?
So, the letters in the total equation, so you're going to put the total number of what it came out to in the balanced equation, not just like what it shows there.
The reason why we put like 6, for instance, for potassium was there's 2 potassium ions, right? Every 1 molecule, but there's 3 molecules of the K2S. So in total, what you have is 6 ions. That makes sense? All right. Any other questions? Speak now or cry during the test. Which is up to you. Yeah. Yeah, it's a solid, so it's insoluble. It doesn't break up into any ions. There's no need to put any charges or anything. Anything else? No question is a dumb question unless it's actually a dumb question. All right, cool. Want to do another one? Pick one to do, 10, 11, or 12. Deal. 10? Sure. All right, so barium nitrate, ammonium phosphate. I need a brave volunteer again to give me the chemical formulas for both of these. NO3, you're missing one thing.
The charge of barium.
Negative.
That's 2, right? So what? There you go.
There we go. BaNO3 2. And ammonium phosphate. What's that going to be? NH4, C3, 4. Right. Nicholas, what are my products?
Barium, phosphate.
Give me the formula, bro.
Um,
Close, missing some numbers. What's the charge of phosphate?
okay. BA.
There's a number in front of the negative. Yeah, so it's BA3, PO4. And then the final one here, BA3, PO4, that would just be what? Ammonium nitrate, right? NH4 and right. Now for our physical states, this aqueous. Which one is my solid, Colin? Barium phosphate or ammonium nitrate? Why is that? Yeah, those things aren't soluble at all, except for group 1 and ammonia. And then this, ammonium's always soluble, nitrate's always soluble. This is like soluble squared. So, right. Another brave volunteer. This equation balanced. How do we make it balanced? Pretty difficult one to balance. Yeah. Three, 2, 1, 6. Those are the balance equation. Now let's check if this is right. 3 bariums, we're good. 6 nitrates, 6 nitrates, good. 6 ammoniums, 6 ammoniums, good. 2 phosphates, 2 phosphates, good. And yeah, I think I checked everything at that point. All right, this is the balanced chemical equation. Go off to the side here. Let's write our total ionic. All right. All right, so sorry. So you asked me about the ions.
Okay, asking me for the whole thing?
Yep.
I can't do the whole thing, but I remember from what I asked, so it's gonna be 3A aqueous?
That is it. All right, keep going.
No. I can't work that fast.
Give me a bit of time. Minus something, not 1 minus. 3 minus. So the next one wouldn't be PO4 though, because, or I guess you can put it, but I like to go in order. Start with the nitrates. How many nitrates we got? 6NO3 minus. So 6NO3 minus this. All right. How many ammoniums we got? 6 NH4 plus. Aqueous. All right. Now, Nick, what are the phosphates?
It's 4, 3 minus.
PO4 3 minus, and how many are there? 2 PO4 3 minus aqueous. And we split up our solid at all in ions? No, so we just write that out. Pa3, PO4 solid. And we do the same thing, 6NH4 plus aqueous plus 6NO3 minus. All right, what do we do now? Delete the spectators. Spectators. So, lucid dreams, scared of love, robbery, and I don't know any more musical songs. Right. I said goodbye, good riddance the last time, so I'm a funny guy. All right. So we have canceled out the spectator ions. So what is our net ionic equation?
That's
A3 PO4 2. Net ionic equation. All right. Y'all good on these or more? All chilling.
How do y'all feel about intensive and extensive properties?
extensive depends how much you have, and then intensive doesn't.
All right, Nick. Give me some examples of some extensive properties.
Mass would be extensive.
Correct.
Would density as well. But density
That's
it's
correct.
like have the elements as dense.
Density, it doesn't matter how much you have. Density of 1 glass bead equal to the density of 18 glass beads.
Yes. The water, and like if you pour them in water,
What are some more extensive properties? That volume's 1. What about color? Extensive or intensive?
yellow is yellow.
Yeah, it doesn't matter. Like my shirt, gray. It doesn't matter how much gray is on my shirt. Like you can tell I have a gray shirt. Gray. I mean,
That was good.
I don't know. I'm probably colorblind or something. I don't know. I think 1 in like 5 males are colorblind or something like that. Genetics. That's what I remember. All right. Shape. What about shape?
That's
Yeah, because a square is a square. It doesn't
Yeah,
matter how many
square is
squares you have. So shape. All right. Give me some more extensive properties. Size.
yeah.
Which one's that one? Extensive or intensive?
That's intensive though. Like, have like 3 moles of one thing, it's still gonna be the same.
What's everything?
I mean, yeah, I was gonna say, if you have like 3 elephants, they'd all be like the same size, assuming they're the same species of elephants.
So it doesn't make a difference if you're talking about them individually.
Well, I guess thing is like extensive, you talk about them like in a group versus intensive, it doesn't matter whether you talk about them. So
There could be yellow here.
Yeah, because the size can change, right? If you have a pound of gold, 2 pounds of gold, still gold, but the size is going to differ. So it's going to be dependent on the amount of matter present. So it's going to be extensive.
area,
Yeah.
I mean, area again, yeah, it's an extensive one. Because you could have like a 2x2 enclosure or like a 3x3 enclosure. And that
What about flammability?
That'd be intensive. Be the same.
Yeah,
For
you're right.
intensive, you could also put
force.
Boiling point would be intensive as well.
So we have flammability in the intensive category. Boiling point, why do you say boiling point?
Because if you have like this much water and that much water, it's still gonna boil at the temperature.
What is that temperature, by the way? You're gonna need to know it for this class. 100 what?
Celsius.
Celsius, yeah.
What is it in Fahrenheit? Well, you know. Yeah, it's 212. All right, yeah.
Yeah, it was.
Well,
Well, that's a whole set of that's a whole another branch.
I think because in this case, when it was introduced in class, it was described as like a. So I guess in flammability.
But flammability is indeed a chemical property. You are right, because I mean, look at combustion reactions. If you heat them up, it literally changes the composition of the elements. So you don't have like your hydrocarbon anymore. You have like carbon dioxide and water. That's why flammability is chemical. But yeah, we have mass, size, volume, area, density, color, shape, flammability. Any more intensive and extensive properties of it?
The hardness, luster, maybe.
Hardness, luster. That all doesn't depend, right, on the amount added. It's like gold will be the same hardness, regardless if you have 1 pound or 3 pounds. Yeah. Yeah, I would say so, because if it's 32 degrees, you'll feel cold. And if it's 100 degrees, you'll feel hot. So, temperature.
there may be like weird elements that don't exist on the test, like a new element like Armenium. And then you have to find like how many isotopes medium has or something. Yeah.
Possibly, maybe. I can neither confirm nor deny that is on the test. All right, yeah. Yeah, I think you will need to know that. So anything in its elemental form has what oxidation state? And any polyatomic ion, so say for example it was like nitrate, what's the oxidation number going to be equal to overall?
0.
Charge. So it'd be equal to -1.
You meant like it's like a compound in general. Like yeah.
Oh yeah. Like a neutral compound, you're right, that would be. So
charge.
Yeah.
Oxygen is always what?
Zero. Oh, this is a -2.
-2.
Or 2 minus.
Well, what if it was O2?
Then there's 0.
Then it's
how you
0.
get.
There we go.
We're gonna go over a problem from the exam review. That's cool with y'all. Are you done with the intensive extensive, or do you want to go keep going?
Y'all all good on intensive extensive? All right, that was the only question I missed on my test, so kind of haunts me to this day.
All right, so how many of y'all are in Dr. Armand's class? How many? Okay, so a good amount of y'all might have not seen this question, so that's good. I'll change up the numbers just a little bit so that way it's new to y'all, and I'll change up the problem. So what? Grams the that contain what is the mass in grams of this specific compound? What is the name of this compound?
That a P?
That is a P. Are you making fun of my P's?
What the question, sorry?
It's up there. Oh, so what is the name of the compound? pH3. It has a more common name. So if you're going to go through the regular covalent compound method, that's more like the covalent scheme of name. So this is a common name. So think of NH3. We call this ammonia. So this is similar in that it has common name. Anyone know what it is? Well, phosphate is PO43 minus. It's phosphine.
Chemistry is weird. There's a phosphate, a phosphine, a phosgene. Yeah.
Yeah, so phosphine. And the molar mass of phosphine, molar mass ratio.
That's 34.
All right, so how would we go about this problem?
Our like determine our we already it's 34 grams and multiply that by turn that into atoms.
Well, usually what I do is I start with what's given.
There we go. Start with what's given. So 8.22 times 10 to the 26. And these units are hydrogen atoms. So start with what you're given and put that over one, or do your train track method or whatever. Start canceling units. So we know there's a special number we're going to have to use. We're given atoms. We're asked for grams. So in chemistry, atoms, there's an intermediate that we have to get to before we can go straight from grams to atoms. That intermediate. Yeah, so moles, right? And from moles to get to atoms, we just use Avogadro's number. So here we're using the number, and here, what do you think we're using over here? Molar mass. All right. So right now we're given grams, or we're given atoms, and we need to get to grams. So first we got to get to moles. So moles of what? Well, we can just we're gonna use Avogadro's number on the bottom, and we know that there's 6.022 times 10 to the third H atoms in 1 mole of hydrogen atoms. Right? That makes sense? Next step here.
3 moles of each.
Yeah, so there's 3 moles of hydrogen in 1 mole of phosphine, pH3. That makes sense? This highlighted step makes sense? Yeah, it's just a ratio. That's all it is. And so next, we're just going to use, well, we're in moles and we want to get to grams, so we use the molar mass. Molar mass is 34 grams every 1 mole And we'll do this in their account. Okay. And I didn't hear you. You're all the way back there.
1.54.
1.54 times 10 to a lot of grams. All right. Everyone get the same answer or fact check column? Okay. All good. This type of problem makes sense. These problems are really good when it comes to preparing for the exam because y'all know who makes the exams? Dr. Armand. Know who made this review? Dr. Armand. So he makes the exam, he makes this review. So it's really good if you know someone in the class. If you're not in Dr. Armand's class, you gotta know someone in that class and then get the review from them. Start practicing those questions. Okay. Yeah, so there's plenty of people in Armand's class here. There's plenty of people that are not in that class, so start getting each other's phone number or whatever and make a group chat or something. Okay, so don't cheat in the group chat. Share knowledge. Whatever.
If you cheat, I will find you.
We got 11 more minutes. What else do you want to go over? Or do y'all have questions on something you saw and you want to throw that up here?
Well, I know there's stuff from unit like 2. What specific? I know they sent out the learning.
All right. Well, if you find out, then you can say it. Okay. Do you have a question? Stoichiometry? Sure. Yeah. All right, between 9, 10, and 11, which one would y'all want to do? Yes. And yes, and all right, we'll do number 10 because that's a percent yield question. And you will most likely see a percent yield question. You may see a isotope question. Most likely.
Very similar to what I posted in the group meet, I think yesterday.
Yeah.
Worked for that.
Well, that's just the isotope minus.
Oh yeah.
Yeah.
No, but we're talking about a more complex problem. All right. Reaction of 7.8 grams of benzene C6H6 with excess nitric acid resulted in 0.9 grams of water. What is the percentage or percent yield? Nice, they gave us the molar masses. I cannot guarantee that they'll be given to you on the exam. So make sure you know how to do that. Is this equation balanced? Is the next thing we should be asking ourselves. Is it balanced? Let's balance. Yeah. All right. Next step. Do we need to figure out the limiting reactant? And why do you say no? Yeah, it tells us that it's excess. It only gave us the mass of one of the reactants and told us the other is excess. So that when you see that, you're gonna be thanking Dr. Armand for not making you calculate limiting reactant. Okay? So 7.8 grams of benzene, that's all we have to work with. There's no limiting reactants that we have to find because benzene is the limiting reactant. All right, so 7.8 grams. What's the molar mass of benzene? 78 grams, 1 mole. Six. And what's next?
Molar molar ratio to go.
Okay, so we're going to water. So and it's a 1-to-1 ratio. So again, you don't have to write this step out if you realize it's a 1-to-1 ratio. I just do it because one, I like to see all the units cancel out. And you don't have to. I do it for teaching purposes, so I don't do it. 1 mole of water has a molar mass of 18 grams. What do y'all get when you put it into the calculator?
Yep. 1.8.
1.8 grams of water.
So
H2. Yeah, 1.8 grams of H2. All right. Now are we done yet? No, so we're asking for percent yield. So we know that equation is actual over theoretical times 100. What we calculated was our theoretical. What we were given in the problem was our actual. So 0.9 divided by 1.8 times 100, 50%. Got a 50% yield. This is recorded, so I don't know if you plan on trying to upload it before the test or not.
I probably will, but it takes like 2 hours to process, so expect it around like 5 or 6.
So you take pictures and want to kind of go through the process again later, check out that video. All right. I like to reserve the last couple of minutes just if you want to come up and do you have any questions about something you were studying or regarding anything? So yeah, what's up? Yeah. Yeah, if it says that the nitric acid is the excess, that automatically means that the benzene is the limiting reactant. So we don't have to find the limiting reactant because we know what the limiting reactant is. Yeah, exactly. So you don't, and also you're not given the mass of 2 or more reactants to calculate the limiting reactant. So you would need to have more than one masses per reactant.
But if you were to, like, if you needed to find, could you just stop at moles instead of having?
Oh yeah, you can stop at moles because you'll save that. Yeah, you'll find which one's less, and you'll save a little bit of time when you cut. Yeah.
That's how I do it personally. I'd stop at moles.
Was that?
I stop at moles personally. That's how I do it.
Unless you're calculating for